Hello, can you hear me? Yes. So welcome everyone to this chemistry seminar number 3, which will be about the MAX4 laboratory and presented by Professor Jesper Andersen from MAX4 laboratory. I don't know if you want to introduce some of your own activities, but I think I just hand over the word to you, or maybe I do not. First of all, before doing that, we have some 4 other representatives for the MAX4 laboratory here today. And after this talk, there will be some informal discussions, I hope, continuing over in building 206 in room 27 or something. At the bottom floor anyway. Follow the stream.
Okay, thank you, Kenny. Very nice being here back in the old country and at DTU chemistry. I'll tell you about the MAX4 laboratory and why we think it is new light for science. I hope I'll convince you that that is what it is. You can answer what is the MAX4 laboratory by saying it's the most ambitious and it's the largest ever Swedish investment in research infrastructure. You can also start to look at what it is, and it's a new synchrotron light facility being built in Lund. It will be the brightest light source around. It therefore has the potential to actually become the best synchrotron radiation laboratory because of this fantastic light source. And then for DTU, it has the further advantage that it is actually virtually on the doorstep of DTU. Going to Lund is roughly an hour. You can do it faster if you break the speed limit. But that is what it is, and when you go there in a short year from now, actually even if you go there today, it will look like this on the outside. This is the highway to Denmark. Here's a map. This is central Lund. Here's the highway. Here is the MAX4 laboratory. This, some kilometers further up or down the road, is where ESS, the European Spallation Source, will be built some 4 or 5 years after we have started operating in the MAX4 laboratory. The current MAX laboratory is placed down here close to campus. Again, I pointed out to you that from Lundby to Lund is roughly an hour. That was geography. Then what are our ambitions? And well, we want to serve all fields of science. We want, and we think we have the potential to do it at the international forefront. We will provide a very high level of service for the users, also because all fields of science imply that there will be many users who are not physicists or chemists. They really don't know anything about synchrotron radiation, what it is and how they handle the equipment, but they have very many interesting scientific problems. For that, we need to supply very high level of service. During the beam time is one thing, but also for the analysis afterwards. We are currently formally a national facility, but we want to be an international facility. And of course, we will serve Sweden and then the neighbors, Scandinavia, and then also the rest of the world. We will actively seek new ideas and partnerships we will be a powerhouse for research-intensive innovation, and until we start Max 4, we will still operate Max 1 to 3, the current facilities. But I wanted to highlight these, that we will be an international facility that serves Sweden, the neighbors, and the rest of the world, and will actively seek new ideas and partnerships. Now, that also means, or put a different way, we want to expand the Max 4 laboratory and offer partnerships to, in particular, Nordic and Baltic partners. That can be countries, that can be universities. I'll give you a few examples, very brief, that we have been successful on that. Now, there is this facility. How could you get access to it? And I always forget to do this, so I just wrote this down 10 minutes ago. But you can apply to the facility to get beam time. Typically, it's open twice per year, and then your applications are reviewed. The two sole criteria we have are scientific excellence and feasibility. Nothing about nationality, nothing about if you have paid for the facility. And furthermore, there's no charge for the beam time. Of course, it comes with a cost for you. Well, for you, it's the gas to go these 50 kilometers, but that's all. Then, of course, there's a possibility that you could buy beam time. Typically, industry will do that, and then we have no demands that results are published afterwards. Then I added this also, that partners, countries, institutions that contribute to the facility, they can get privileged beam time, of course, somehow in relation to the contribution they make. Okay, history. Max 4, of course, comes after Max 1, 2, and 3, as all of you have guessed, and that was called Max Lab. It has existed since 1987 in Lund, and this is how it looked, I think, a year ago. Here are the user statistics as a function of year. 87, 88, we started with 100 users per year. Now we have per year 1,000 users, roughly, that come in and use the facility. They are, if we look at the Swedish users, well distributed among the Swedish universities. Of course, Lund has a major part, roughly a third, but all other universities are represented. And if you look at the distribution internationally, and this is the number of users, it changes slightly if we take the beam time, but only slightly, then 40 to 50% are from Sweden. 20% actually comes from Denmark. And well, then if we add the other Nordic and Baltic countries, we come up to roughly 75%. The remaining 25% are from the rest of the world. So in many senses of the word, we are an international facility already today. The methods at Max Lab, well, they have necessarily a focus on the soft X-ray regime because Max 4 is a 1.5 GeV ring. So there are lots of soft X-ray spectroscopies, and there I would dare to say that Sweden is among the world leaders in soft X-ray spectroscopies. I mean, XAFS was developed in Uppsala, and it's been a long tradition. Soft X-ray microscopy, IR microscopy. Then there are a number of hard X-ray techniques, XAVs, X-ray absorption, SACs, X-ray diffraction, including also protein diffraction. We have those, but I mean, because of the machine, we are not excellent. That will change in the future. The future is MAX4. And this is just an overview of how it will look. Here's the linear accelerator, and then there are 2 storage rings. I'll come back to this in more detail, but I just wanted to point out that there are actually 3 radiation sources there, which have different properties, so we can cover the full energy range, and we can also cover the full time range. We can actually do time result down to femtosecond regime measurements. I said at some point that MAX4 is the best machine. And here's the proof, whatever you want to call it, of that. There is one parameter which you look at when you look at a light source, the brilliance. That is how well collimated is the light and how small is the light source. That's what you go for. Here is the brilliance or the angular spectral flux for MAX4, NSLS2, which is being built at Brookhaven, and the rest of these are existing machines. As you would have guessed, I wouldn't have shown this figure if we weren't on top of everybody. So, and in particular, I mean, don't miss down here, just coming over the bottom line is MAX2, and just count the orders of magnitude that we gain in brilliance. And then this is soft X-rays. I mean, I think it would be below the floor here for the hard X-rays. Imagine that gain. Timeline, when is this wonderful thing going to work? Well, again, history. In 2009, we got the basic funding. 2011, we got the first beamlines. Now we are in 2014. And the LINAC, this linear accelerator, they are actually either this week or next week starting to run electrons there. It's been mounted, it's been tested. They are hoping to have the first electron pass through it in a week or so. This year also we'll start to mount the rings, and by the end of the year we will start to commission what I call femtomax. I'll come back to that, but the first beamline actually using the LINAC. Next year, the LINAC and femtomax will be in operation. The rings will be commissioned, and we will move into this new office building. And we will start mounting the beamlines. 2016 is when the rings go into operation, and well, the first 8 beamlines will be in operation. After that, well, we will add more beamlines, we'll develop the facility further, all the necessary auxiliary laboratories that have to be around it. And there, remember also that we might have large synergy effects with ESS. They will need the same kind of auxiliary equipment as we will. So there is a possibility for making use of that. And then here it says free electron laser. We have a possibility, since we chose, and that is the reason why we chose a linear accelerator as injector, we have a possibility to add a few hundred more meters of linear accelerator and build a free electron laser. We would need 1 billion kroner. It really doesn't matter if they're Danish or Swedish. I would prefer Danish. And we would need some 8 or 10 years before that is done. But a free electron laser is in our strategic plans, and we talk of a year like 2022 is when it could become operational. Now, here, late 2015, actually on the 13th of December, because that is Lucia Day, which is big in Sweden. It's a Sunday. We will close the existing Max Lab. 21st of June 2016, we will inaugurate the Max 4 facility. So there's half a year here where Sweden will be terribly dark. And all the researchers will have time to write all the papers they never had time to write because they went to Max and did experiments. Let's go back to this, the big deal about Max 4. And, well, it actually is all about the brilliance. This is Bertha Röntgen's hand, and this is Bertha Röntgen, her man. And you all remember Röntgen was discovered back here. And for 50, 60 years, nothing happened to the brilliance. Then, in the 60s, well, rotating anodes were developed, but in particular, people started using storage rings parasitically for producing synchrotron radiation. And then this red curve is the development of the brilliance over the years. Max 4 is here at the top. And just for the fun of it, I put in Moore's law for semiconductors, and you can see we beat it easily. So then you can ask, in particular, if you know Max Lab, we are not a big laboratory. We are rather very small, and we are very lean. How is it possible that we can do something like this? And actually, all the reasons for it are here. The major reason, in my opinion, is Mikael Eriksson, who's our accelerator physics professor and machine director who struck on these ideas. Now, the brilliance, that is 1 divided by something called the emittance squared. Now, the emittance is some constant which depends on the details of the machine. Then it's the electron energy squared, and then it's divided by the cube of the number of magnets. Now, if I asked any of you to influence this and maximize it, you would say, well, let's change the number of magnets. That is what Mikael came upon, but if we do like this, then this, which you maybe not can see, this is a typical storage ring, old-fashioned technology. From here to there is some 10 meters. Those 10 meters, Mikael have by doing multifunction and miniature magnets been able to squeeze into roughly 1 meter. That is necessary to increase the number of magnets unless you want to end up with a huge machine which is 5 or 10 kilometers in diameter. So these are the basic ideas that makes the Max 4 such a hot topic among accelerator physics and people who build synchrotron radiation facilities these days. So we can say we are the best. Now, it's very easy to say we are the best. There's one good test of it. If everybody else copies you, then you are pretty sure that you are the best. Here's one example from Nature. Yeah, this is Nature, not Science. This is about the ultimate upgrade of a US synchrotron. This is the Advanced Photon Source in Chicago. They had an upgrade program which, as far as I can read here, is 391 million US dollars. This was in Nature about an American storage ring and their upgrade. What's yellow marked here are all the things that deal with Max 4 in that Nature paper. That was a Scientific American paper on this also. And what did this lead to? Well, it led to DOE deciding last year, we stop that upgrade program. Before you can restart it, you have to change to, this means multi-band achromat, which is that idea of increasing the number of magnets. When we look around us today, all facilities that have upgrade programs, they use the Max 4 lattices. We are pretty confident that we are the best. Will not be for long because everybody else is pushing ahead with similar programs. Now, just a little bit about the inside of the ring. Is that we have a LINAC here that can inject into a 3 GeV storage ring, and it can inject into a 1.5 GeV storage ring. The 3 GeV storage ring is a very good ring for, let's call it hard, soft X-rays, and for X-rays. And it will be the brightest ring-based light source. I'll come into a figure showing the beam lines, but for now I just wanted to point out that when the capacity is what we would call fully utilized, some 10 years after we have inaugurated the facility, we will have some 25 or 26 beam lines. We could squeeze a few more in there, but we don't see the need for it. This is what we are aiming for. Now, here's what I promised. The detail, well, not details, but at least the 13, or actually now it is kind of 14 funded beam lines. The first one here, FemtoMax, that is a beam line at the end of the LINAC. We can compress the electron bunches in the LINAC to less than 100 femtoseconds. Then we send them through an insertion device, and then we get flashes of light out that have 100 femtosecond in length. Or we can actually, we hope that we can squeeze them down a factor of 2 or 3 more. 100 femtoseconds is what we promise. Those light pulses will actually be hard X-rays. It goes from a few keV and up to 10, 12 keV. You can do time-resolved diffraction. The difference between FemtoMax and a free electron laser is that we have quite a short length of undulators, so we never go to lasing, we never go to stimulated emission. That means that we have a factor of 10 to the 4, roughly, maybe 10 to the 5, less photons per pulse. We still know that the intensity we have is sufficient to do time-resolved diffraction. We know that because people also do that at what's called slicing sources, and they have a factor of 10 lower intensity than we will have here. And the other difference is from a free electron laser, the radiation you get out is 100% coherent. It's not here. This is spontaneous emission. That in some cases actually is an advantage. Okay, then enough about Femtomax. Nanomax, I'll come back to. It's a nano imaging beamline. Balder, which actually should be pronounced Balder, because Balder is the Nordic god for light. It doesn't refer to anybody getting older. Is an XAFS, or X-ray absorption spectroscopy beamline, where the emphasis will be on in situ and time-resolved studies, and where we also will aim for some of the things some of us discussed today, actually being able to distinguish signals from low-density samples. So various schemes for that. Biomax, which is protein crystallography, I'll show you more about that. Veritas, which is soft X-ray beamline, but still under, it's actually this one, no, this one, sorry, on the 3GV ring, which will be a unique beamline for resonant inelastic X-ray scattering in the soft X-ray regime, which is a way to look at electronic structure. Photon in, photon out. HIPI, which is a high-pressure photoelectron spectroscopy beamline. I should have time to come back to that. ARPES, angle resolved photoemission. And then a beamline called finest beams. Let's not talk about what it can do, but it's called finest, not finest, because it is funded from Finland and Estonia. That was the first international beamline, the first two countries that became partners. There are a couple of other soft X-ray beamlines that will actually be transferred to the 1.5 GeV ring, including a photoelectron microscope with an ultimate resolution of some few nanometers. And then there are beamlines that would be of interest to people here. It's called COSAX, but it's a SAX beamline where there also will be possibilities for coherent imaging. There's a beamline called Softimax, also imaging. I'll come back to that. And then this in parenthesis, 14 is a beamline called Danmarks, which is a Danish beamline for powder diffraction and for imaging, and which on the 24th of March actually obtained funding in the NUFI process. And then I put these in, which are two beamlines that we don't have funded, but which I can see again from our discussions today could be very interesting for you. There's a Micromax beamline, which is a submicron focus beamline for protein crystallography, but protein crystallography in the form of serial crystallography. So you don't mount your samples, you have them come in a liquid jet. This is very much what is done when you do protein crystallography at free electron lasers. This is a development that even can make a physicist like me very excited. There's also a beamline, MedMax, which is biomedical imaging and for samples. And samples can also be living rats or mice up to 10 centimeters. Okay, Biomax, protein crystallography. And that's a very simple beamline, just a double crystal monochromator, and then a KB mirror for focusing, and then you can get a focus which is 20 to 100 micron. You can actually move away, so you can defocus if you want to do that. Will have very high flux. It'll be a highly automated beamline. This is high throughput protein crystallography. And just to, well, yeah, your good old protein crystallography, but very fast, very highly automated. I thought I would show you how it looked a year ago. And, well, this is actually water here, so you can see the advantage of putting a roof there. They did that. And this is actually how it looked a couple of days ago. And this then is how the computer picture shows us that it will look in 2016. Let's go on to the next beamline, which is something completely different, the Softimax beamline. That is a beamline for imaging in the soft X-ray regime. It has two branches. One of them is STIXM, scan transmission X-ray microscopy. You focus your X-ray beam down, and the focus is in the 10 nanometer range, and then you simply scan your sample, and you have a detector that looks at this. And there you can pick different kinds of detectors depending on what you're looking at. This is in the soft X-ray regime, so you can actually use chemical shifts to give you contrast. Now, a chemical shift means that various molecules, some protein, sugar, a lipid, they actually have different absorption edges and at different energy positions. So you can easily see that if you sit on this, then you can map where are the proteins. If you sit here, where are the sugar, where's the lipid, if you sit on this. So that's a scanning method. The other method on that beamline, which is coherent imaging, is a full field method. You can say this is a way of doing imaging without a lens. So what is done here is that you use a pinhole, and then after that you get a coherent, coherent light. You let that hit your sample, and you detect the scattered intensity. One thing here, for because of the high brightness, we will have a very coherent X-rays. For soft X-rays, 10% of the X-rays we get at 1 kV are coherent. If you go down to 300 eV, it's 30%. If you look at other facilities, it's percent or below percent. But anyway, that helps you a lot if you have very much coherence in the radiation here. Then many of you know that to get from this and back to how did my structure look like, it's the phase problem. You have to find that in scattering. And there are various ways of solving that, either various iterative algorithms, either coherent diffraction imaging or chukotrophy oversampling. And so you can do that, and sometimes it converges, sometimes it doesn't converge. There's another way of doing it, and that is actually that you can encode a phase. So here you would make, typically you would make a small hole in your sample here, so that on the back side here emits a reference beam, and then you get the interference between that and your scattered signal, and then it's just the normal Fourier back transform holography. So this, again, also is in the soft X-ray regime, so we have chemical from the chemical shifts, or you can play with magnetism, you can have magnetic contrast. Anything that basically scatters soft X-rays differently, you can use as a contrast mechanism. Ultimate resolution is 10 nanometers or below. It's full field, which, by the way, also means that it's excellent for time-resolved studies. Maybe not in the femtosecond range, but very fast. here's just one example where these are various different magnetic nanostructures. I can't remember what material, but then how you can follow that various of these particles become magnetites, whereas others don't. And this can actually be done time resolved. A few other examples. This has been used for looking at skeletons of small algae. This was, and it can actually be done in a tomographic mode, so you get the 3D structure. Or here, there is, these are actually yeast cells, and this is, again, CXI, or CDI, and resolutions down in some 20, 30 nanometers, full field. Nanomax imaging beamline hard X-ray regime. Here's the commercial page. We can do very much of this in situ conditions. For instance, here, if you have a catalyst, you have a gas flow, you can look at that. Or this is a particular example where the catalyst actually would be small gold particles, and you grow nanowires. You can look at biochemistry, cell nanostructure interactions. You can do hardcore physics, and you can look at biostructures. This beamline will look like this. We have an undulator as the insertion source, and then some optics. And then here, using zone plates, there will be one experimental station where the ultimate focus we are aiming at is 10 nanometers. That definitely will not be 2016. 2016, it will be some 30 nanometers. There's another experimental station where the requirements are much less relaxed, and there we go for 200 nanometer focus and just normal KB optics. Now, there are other facilities that say they can do this, they will do this. This is 100 meters. We can do with just 100 meters because we start with such a fantastic wing, such a small and well-focused light beam. Other places do this 200 or 300 meters. You need that to get to that kind of focus. There'll be, again, you can focus it, and then you can use various different detectors that detect different signals. Fluorescence, then you could scan your sample and get the elemental composition. You could do diffraction, then you can get the structure of the various parts here. Or, well, you can also look at a Sachs-like signal, or you can do coherent diffraction. There are a lot of things to do, and we will implement quite many of these, and we will implement them sequentially. One thing you could look at here, this is not limited to 2D. You can also do it three-dimensional. And this is just an example of something that you might call low technology cement, but how cement solidifies and how you hydrate the various components, what isn't hydrated, and the porosity in it. And this is something I took from the Swiss light source. What they can do today is to make a complete three-dimensional picture of such a structure with a resolution of some 30 nanometers. Much of that resolution is actually set by mechanical precision. You can imagine rotating. You have to rotate the sample to do these tomograms. Do that without it wobbling some 10 or 20 or 30 nanometers. But this is what can be done today. And see, this is actually a small sample, some 10th of a millimeter. But millimeter, maybe up to centimeter sized samples are what we can do. I'll show you a little about the Max 4 Hippie also, which is a high pressure and high resolution electron spectroscopy. And I mean, I come from surface science, and their pressures are typically in 10 to the minus 10, so millibar. This is up to 10 millibar. So that is why I call it, or we call it, high pressure. Many others would call it still low pressure. But it is pressures where the chemical potentials often are such that you can actually identify all the important processes that would happen when a catalyst is working. Not in all cases, but in many cases. And remember, the vapor pressure of water at room temperature is some 25 millibar. So you can, in such an instrument, if you can go up to 25 millibar, and we can do that, you can actually study stuff under wet conditions. What this is about is simply you send X-rays in, hit your sample, you detect the electrons that come out. This has typically been done in UHV. There are tricks so that now you can actually do it in pressures up to 50 millibar. Why is it important to look at those photoelectrons? Well, it is that because from an analysis of the spectra, this is of a palladium and this is of oxygen, you can deduce very much about how does this surface look like. DFT is very helpful in doing that, or in extracting exactly what is happening. I took a very much a standard example, CO oxidation on platinum of that actually work that we have done at Max, but this has been done elsewhere. But just to show you what you can do. This region is where you find the oxygen 1s. There are these two peaks, which is from the oxygen molecule in gas phase. And here, when you are below 530 Kelvin, you find two peaks from oxygen from molecules adsorbed on the surface. We know, everybody knows that these two guys are CO sitting in two different adsorption sites on the surface. We also, if we look down there, we see that this is the gas composition measured simultaneously with this, that there's no CO2 production. If we go above 530 Kelvin, suddenly we see CO2 production starts. And then we look again at the oxygen, and we see we have oxygen O2 in gas phase. We can actually also see the CO2 in gas phase. But then look here, those CO peaks have gone. Instead, there's a peak here at 500, just below 530 eV, which we know is oxygen on the surface. So everybody knows that platinum is a good catalyst for CO oxidation, but this is actually what shows that it's platinum with adsorbed oxygen that is the good catalyst. Admittedly, this is a very simple example, but here we can see what is the state of the catalyst when it is active. I could have picked out spectra also where we would have looked at the platinum or in other systems. This is a very, very useful method to follow the actives, or to detect the active state of catalysts. There has been very much work in this field over the last 10 years, and much of it have shown that the previous understandings in surface science actually should not be called understandings, but misunderstandings. And this is a very important area. So now I went back to this just to show you that I've shown you roughly a third of the beamlines that are funded and that are going to be built there. The first 8 of them will be operational in 2016. The remaining will come along in 17 and early 18. We can sum it up this way also, that Max 4, because of this world-leading brightness, we have the best coherence in X-rays that you can get in the world, apart from a free electron laser. And we have this ability to focus to a very small beam spot very easily. We don't need long beam lines with all that implies. We also, because of the choice of a linear accelerator, we can do femtosecond studies. And then, well, use coherence. Now we can cover not just IR and soft X-rays, we can cover up to quite hard X-rays. Femtosecond, we can get a very high spatial resolution. We can, because we have so much intensity, we can easily go from 2D to 3D. You know, every time you add a dimension, it takes so much longer, simply because you have to do more measurements. That becomes possible. And 4D imaging is, of course, that in some admittedly favorable cases, we will be able to do tomography with time resolution. Spectroscopies, scattering and diffraction, the classical methods, we can do better than done anywhere else. So if I should sum it up, then we can do imaging at length scales down to nanometers. We can pick whatever contrast mechanism there is for X-rays. We can do it under in situ conditions, and we can actually do it pretty fast, and in some cases pretty fast means 100 femtoseconds, but else sufficiently fast that we can follow many chemical processes. To me, a machine that can do this is actually the ultimate instrument for investigating materials. What is in my material? What is its structure? How is its electronic state, magnetic state, so on and so forth? And I should say also then, in materials, normally I don't use materials. I normally write stuff. And then I explain to people that if I say materials, and I'm among people from medicine, they say, oh, you are just a physicist. So stuff is a good word. I wrote materials here and wanted to point out to you that for me, materials is also tissue, biological materials. This is the ultimate machine for that. Then I just have a couple of things left to say that the Max 4 inauguration will be Tuesday, 21st of June, 2016, noon. And this is noon local astronomical time. And of course, you know why we have picked this. That is because that is the brightest time of the year for the brightest machine to be used by the brightest researchers. So you are all very welcome to that. And this is our current funders, where I was very happy to actually be able to add Dannebro to this very recently. And then I'll just say thanks and show you the picture of how the thing looked less than a month ago. Thanks for your attention.
I will guess there are some questions.
Okay, since I'm a frequent user of Cassiopeia, and we see that it's we get one beamline instead, I suppose the capacity will be much larger of the new beamline, or different?
Well, you could say it's the same number of beamlines, because Cassiopeia, I assume you are thinking of the SAX beamline.
No, I'm actually thinking of the MX.
Okay, but again, I mean, even though there are 4 or 5, depending on how you count, end stations at the same beamline, they're kind of independent. So in some sense of the word, you don't get more capacity, because there will just be one. But when you then consider that you have probably 1,000, or I don't know, more intensity, in that sense you get much more capacity, both for protein crystallography, but also for SAX.
Okay, thank you for an interesting overview. I have a small question concerning the Femtomax. You mentioned that the time resolution would be of the order of 120 seconds. I know there's, in this probe business, there's also this issue of controlling the time delay between the pump and the probe.
Yes.
So is this delay control, the splitter, that's taken into account when you say 120 seconds? Or?
Yes, it is. But Femtomax doesn't exist yet. On paper, it is taken into account. But it actually is a major issue with this kind of, well, with any pump probe experiment, the jitter between them. Yes, it is taken into account.
I have a very practical question. Except for all these technicalities, will there be any arrangement for dormitories or things like that for visitors, or do we rely on Lund?
Well, let me just find a particular transparency for answering that. I can say that for the Max 4 laboratory, we have no funding, no possibility to invest in guest houses or so. Let's see, where did I have that? Here. Here. See, here is Max 4, and here's ESS. In here, between the two, is a piece of land that is owned by Lund University and Region Skåne. And that is called Science Village Scandinavia. It's an area where businesses can establish themselves, but also where universities can have outstations, and where we are hoping that some investors will actually build a guest house. We do not have the possibility currently to run it ourselves. We are very aware that this is something that the better guest house you have, the better synchrotron radiation laboratory you are. It is very important to have it for the users. You can also see that this is kind of farmland out here. So there are all kinds of discussions in Lund of actually having a tram line going out here. And there are, in the planning for Lund, plans for developing this whole area into some mixture of residential area and high-tech businesses. Right here, Sony, formerly Sony Ericsson, had their Swedish headquarters. Ericsson is established here. Here is the Ideon Science Park. And here actually is Medican village, but there are plans to develop this whole area into the high-tech industry area of Lund. A guest house, we hope for it. We are pushing as much as we can. We'll see.
Thank you. I have another more technical question. The electrons that you generate in the LINAC for this femtomax, has anyone used those electrons to do electron diffraction?
No. To my, I'd never thought of that, but I mean, you could do 3 GeV electron diffraction. I'd never thought of what will diffraction angles be and so, but yeah, maybe one could do that. Never thought of it before.
Oh, okay. Any more questions? But I guess we thank you again.